with Aston Robotics Vision Intelligent System Lab at Aston University, UK. The title of this presentation is Advanced Human-Machine Interventions for Children with Developmental Disorders. When you talk about socially assistive technology for individual systems for humans, the machine must be autonomous and interactive, provide intellectual, social, and emotional care, encourage physical activity, provide entertainment, offer companionship, generate safety reminders, facilitate intellectual stimulation via games or conversation. So in order to accomplish this, to have this socially assistive technology, we have to think about autonomy, interaction, and emotional care. These are extremely relevant for social assistive technology, right? The other topics depend on the context and scenarios that we have the machine interact with humans. So in this presentation, I'm going to present two case studies, okay, related to assistive technology. And this first one is a preliminary work on child-robot interaction. So we have some clinical sessions going on with children with developmental disorder. So the idea is to have some interaction to them, where the robots do some questions, and we have some question and answers, verbal and gestural interaction, as you can see here in the video, imitation, physical interaction. So children get really enthusiastic with the use of technology. So why not using this kind of technology as interface to improve their social interaction, to improve some cognitive abilities. As you can see here, the robot is following a script. However, there's some autonomy, recognizing some images when they're playing some games, speech recognition. We are collecting images from the sensors on board and other sensors in the environment. So basically we are trying to follow this architecture here, okay, with multiple modalities in order to fuse the data and recognize emotions for a better reaction. So it's still ongoing, this work, but we have a lot of data to analyze offline, of course, like facial expressions. I'm going to provide details later on. But so far we got emotional reactions given some questionnaires applied by psychologists. So we could check children and parents' response to this kind of interaction. Most of the time, children, blue, and their parents, in orange, were happy and surprised during interaction. Of course, we detect other emotions, but most of the time they were satisfied. And it's impressive that the parents were more enthusiastic with the use of this kind of technology. But yeah, it's quite good and positive, the acceptance of them. So this I'd like to show you, and I'm going to jump to second case study, and I'm going to be focused on this one because the Engage project, which is an engagement via adaptive game with brain-computer interface, is the one that is funded by the RAS site. So we are using intelligent game with brain-computer interface as intervention, okay? Because we know that games can provide entertainment and stimulate cognitive abilities as well. And we know that children get enthusiastic when they are playing games, and the game can be a vehicle through which children learn about themselves, the environment, and develop social skills. Of course, there are limitations when it comes to children with cognitive impairment and any other kind of disability. So the idea of this project is to have a child interact with a game, okay? So we can measure the brain waves while they are interacting, and we can detect the level of concentration. If the concentration drops, if it's below a certain threshold, the game can adapt and generate visual and auditory stimuli in order to keep the concentration up. Um, the child can control the game by gesture recognition. We are using the lip motion control, and we are recording the face via the webcam for facial expressions recognition. If we detect some negative expression, the game can adapt as well. We have some questions, scientific questions that we want to answer. For instance, do brainwave patterns of concentration levels differ between populations? Children with attention deficit, autism, Down syndrome, non-clinical, adults when playing educational games. Can we use prior knowledge, for instance, data from adult and non-clinical children, to improve models of learning classification of concentration levels? Can emotion really show internal states during the interaction? Because we know that children has different facial expression than adults. So can emotions learned from adult data can be used to detect emotion in children? Are intelligent educational games good tools to support education and health, to help children achieve improvements in concentration levels? Can be used as intervention and as to improve inclusion as well in schools. So we have a lot of things to think about. Jumping to the more technological aspect of this project. So when you talk about facial expression, in both study cases, we are based on previous work, okay, affective facial expression recognition for human-robot interaction. We can check details there, but basically use the data sets of human actors, perform some expressions, and you collect our own data sets to try awaken real emotions. As you can see here, they were watching some videos, emotional ads, news, so that we tried to grab the real emotion, right? So we used classical machine learning classifiers, okay, like support vector machines, random forest, and ensembles like the dynamic Bayesian mixture models to combine multiple classifiers to improve the classification. And we could achieve greater than 85% to classify emotion on the fly. Okay, 83% in specific data sets, but when combined with multiple data sets on the fly, we could improve the performance. And it's quite interesting, as you can see here, the classification going on the fly. Basically, this approach, we are using landmarks, detecting landmarks on the face, extracting some statistical features and temporal features as well, checking previous frames and checking the difference between distance and angles, because when you change the expression, these variables change as well. Combined with other features, we can feed the classifiers in order to recognize this. Okay, more details we can find here. For EEG data classification, we are based on previous works of our group. Okay, so far we can classify over 90% using this Muse low-cost sensor, okay, with 4 channels. So basically what we are doing is using a temporal slide window over the different channels to extract statistical features and fast Fourier transform to detect these features as well. And we do some feature selection to keep only the relevant ones, okay? And once we have the features, we try to build an image like this one. So these images are the features of concentration levels, so that we can feed convolutional neural network, deep learning, and the initial layers of this model extract features over their feature space, which means that we are doing some kind of feature selection, getting just relevant information from these images to classify 3 states: concentrated, relaxed, and neutral. We are using Unity game engine, open source, combined with Leap Motion controller, so that the user can use the hands to control. And we are developing games for spelling, reasoning, hand-eye coordination, perception, memory. So one example here, the child can see random images, and then when you see a specific image, the child must select the corresponding letters to write the name of the animal. And we have, for instance, hand-eye coordination, so the child can control the airplane to go up, down, left and right, to get coins and avoid obstacles, this kind of examples that we are implementing. We did some data collection in Brazil with children, with 30 children, 3 different primary schools there, and most of children never touch a computer before, right? And we use 3 games for attention and motor coordination, relaxation, reasoning. 3 minutes of data for each game. We collect lots of data. Okay.
Vai ser muito bom. Vai ser muito bom. Parabéns.
I have an example here of calibration of the sensor to be aware of concentration levels. So we are playing here. The child must find the ball.
Vai lá, agora é minha vez. Vamos, vai lá. Você baralha pra mim.
It's quite interesting because they got really engaged.
Wow. Cara, que rápido.
We have this example here for motor orientation where the child is using the hand to control the game. In this case, he's controlling the airplane. This child has cerebral palsy. We test also with conventional games using mouse to control. Right now, we are not doing classification on the fly. We are just collecting data and the images from facial expression. As you can see, we have some expressions going on. Look, so we have some expressions. So we're trying to collect this data. Okay. Of the EEG data analysis, offline analysis. So what's important to see here? After classifying each child, we can see that the child concentrates better when they use hand gestures to control the game. So they can be most of the time 78% concentrated when using the hands, and 74% when they use the mouse to control the game. Okay, we have lots of analysis to do for each individual. To check when the concentration drops, when we have variation of the concentration. Okay, but this is something that we can show as preliminary results, and also that we did some transfer learning using data from adults to classify children data. So we used the same topology and the weights of the neural networks to improve the classification of children data sets. We could achieve at least 3-4% in performance instead of training from scratch a new neural network for classifying children brainwaves. Okay, so it's something that we're still working on. We did some evaluation in terms of acceptance of the tool. We applied some questionnaires for these children. Most of answers positive, that's easy to play. They prefer to use the hand gestures. It's not uncomfortable, so they can use easily the headset with no problem. They like the game. And the only thing that I think they complained that is a bit tiring, they got tired after using the hand gesture for a long period of time to control the game. Okay. So the impact of this work, we still need to face multiple challenges in order to have an innovative child machine interface, a friendly interface for educational therapy, looking at improving cognitive functions. So what we can say that the smart technology is promising and will be innovative to promote adjustment and development of children. We still need to move towards a fully functional development. We need to integrate on-the-fly facial expressions and on-the-fly brainwaves classification into the game so that the game can adapt. This is under development. So far we just collect the data and did the offline analysis of the data. Okay, but the results of this project will be pioneer. We are going to have a lot of things to show in terms of signatures of brainwaves for different populations, and in long term we want to check if this tool can really improve concentration levels of children and be used for inclusion. Thank you very much.